Hi, I'm Hayden Lee, a postdoc from Hubble University. Today, I would like to talk about some recent theoretical development on the subject of inflationary correlation functions. Over the past few years, there have been a lot of interesting activities in trying to better understand formal aspects of correlation functions in inflation from a new perspective. In this talk, I would like to give a simplified review on this subject based on the three papers that I wrote with my collaborators, Nima Kanihamed at the IAS, Daniel Baumann, D. Pimentel, Carlos Duazo, and Austin Joyce from Amsterdam. Before going into details, let me first talk a bit about the motivation of our work. A fundamental challenge in cosmology is to observe correlation functions of structures like the CMB and isotropies or galaxy clustering in our present universe, and then use this information to reconstruct the past history of the universe that explains the origin of these correlations. The truly amazing fact about our universe we have discovered from the measurement of various two-point correlations is that all structures in the universe seem to have a common origin as tiny quantum fluctuations, which we think were generated during a short period of accelerated expansion at very early times called inflation. Although this is a tremendous achievement itself, to be able to really understand the details of the inflation mechanism, it is imperative to also measure higher point non-Gaussian correlation functions, which live on the boundary of the inflationary spacetime and provide initial conditions for later structure formation. So the fundamental observables that we like to study are higher point non-Gaussian correlation functions during inflation. The conventional method for computing inflationary correlators goes by the name of the in formalism, and it is about computing Feynman diagrams as usual in quantum field theories. Unfortunately, however, this procedure can be rather complicated in general. For example, suppose we want to compute the purely gravitational three-point function of the curvature perturbation zeta. If we naively expand the gravitational action at cubic order in zeta, we get this naively horrifying looking expression, with many of the terms being non-dynamical. Nonetheless, when we reach the end of a lengthy calculation, what we discover is that the final answer for this correlator is vastly simpler than the original Lagrangian that we started with. It's given by this simple expression in terms of the magnitudes of three momenta, and the main dependence, as you can see, can be written as a simple polynomial in the case divided by the total energy E, which is just defined to be the sum over K1, K2, and K3. This result then strongly suggests that there exists a hidden simplicity in the structure of these correlators that is simply obscure in the Lagrangian formalism, and therefore begs for an alternative framework in which this simplicity becomes more manifest. The limitation of the Lagrangian approach is that many Feynman diagrams that contribute to the final answer individually may have no physical meaning, and we only obtain a physically meaningful quantity after summing over many different terms. In retrospect, this simplicity in the final answer is actually hardly surprising. Rather, this has been a recurring theme in other areas of high-energy physics and goes under the umbrella of the bootstrap. Contrary to the traditional Lagrangian formalism, the bootstrap has a totally different philosophy, and its key idea is to use consistency principles to directly determine observables without computing Feynman diagrams or ever writing down Lagrangians. This bootstrap approach, for example, has led to a tremendous progress in the modern studies of scattering amplitudes, which very much motivates us to use a similar bootstrap philosophy to study the structure of cosmological correlators. So in the rest of the talk, I will try to advocate this point of view. First, how does it work for amplitudes? As a simple example, let's quickly recap the structure of the 2-to-2 scattering amplitudes of identical scalar particles with tree exchange. First of all, Lorentz invariance implies that the amplitude must be a function of the Mandelstam variables S and T. The amplitude must also have some sort of singularity that corresponds to an on-shell production of the intermediate particle. And by locality, this can only be a simple pole. And the amplitude has a specific angular dependence given by the Lagrangian polynomial that reflects the spin of the intermediate particle. Although this is a very simple example, it's worth emphasizing that no Lagrangian was needed, but instead simple consistency principles were enough to fully fix the answer. Currently, computing multi-leg processes involving multiple loops lies at the frontier of the subject. It's important to mention that this study is not only of academic interest, but is actually very much motivated by experiments, since precise predictions up to a few loops are actually needed in order to accurately interpret the experimental data coming from the LHC and beyond. So what's the analog of this story for cosmology? In inflation, the symmetries of a quasi-de Sitter spacetime act as an approximate conformal group on boundary correlation functions. The idea behind the cosmological bootstrap is then about exploiting the symmetries and certain known singularity structures as much as possible to directly determine these correlators. For example, from the bootstrap formalism, it is easily understood that three-point functions that arise from contact interactions must take this form given by a polynomial in K1, K2, K3 divided by the total energy to some power. The computation of correlators, however, quickly gets complicated for more general diagrams, and the current frontier of the subject is about understanding this tree-exchange four-point function of massless scalars. Again, our desire to understand the structure of these correlators is very much motivated by experiments, as one of the main science goals of the next generation of cosmological experiments is about measuring these primordial non-Gaussianities. Okay, so the outline for the rest of the talk is the following. First, I will review the basic elements of the cosmological bootstrap formalism. And then I will describe how this formalism can be applied to inflation and discuss some phenomenological aspects of the subject. Finally, I will end with some future outlook. To begin with, let's briefly recall the basic kinematics of the four-point function. First of all, the four-point function in Fourier space has a momentum-conserving delta function due to invariance on the spatial translations. However, there's no time translation symmetry in cosmology, and this leads to a very notable difference between the structure of amplitudes and cosmological correlators. Amplitudes are functions of full momenta, and because there's a full spacetime translation symmetry in flat space, there's also a delta function for the total energy conservation, which for massless particles is just a statement that the magnitudes of the three momenta of scattering particles add up to 0. In cosmology, we don't quite have this extra delta function, but it turns out that there still exists a specific avatar for energy conservation, which is given by a pole in the total energy E. A remarkable consequence of this fact is that because sending E to 0 is essentially enforcing energy conservation, it turns out that the residue of this singularity is precisely given by the corresponding amplitude in flat space. So this provides an extremely strong consistent condition for cosmological correlators. Let's now talk about symmetries. In addition to the usual spatial isometries, correlators in the Sitter space have extra symmetries called dilatations and spatial conformal transformations, which are the analogs of time translations and the boost symmetries of the Poincare group. In Fourier space, imposing invariance under these spatial conformal symmetries gives rise to these differential equations for the four-point function f. It turns out that the action of the conformal symmetries becomes simplest for the so-called conformally coupled scalars that have some specific mass in Hubble units. So let's first analyze the four-point function in this special case, and then I will later describe how this generalizes to other correlation functions. The constraint due to dilatation invariance, the first amongst these two equations, is nothing but the condition that f needs to have a scaling dimension of -1. To solve this constraint, it turns out to be convenient to pull out a factor of the magnitudes of the intermediate momentum ki, as indicated in this picture. The rest of the functional dependence, denoted by f hat here, can then be characterized by just two dimensionless variables, which can be chosen to be the ratios of ki and the sum of two momenta on each side of the four-point function, denoted here by the variables u and v. The differential equations for spatial conformal transformations are difficult to solve in full generality, but they become dramatically simplified for conformal scalars, which take the simple form in terms of the u and v variables we just introduced. Here, these delta u and delta v are some second-order differential operators that take this particular hypergeometric form. This equation is a purely kinematic constraint that enforces conformal symmetry and is therefore non-perturbative. However, we are not yet interested in the fully general solution, but only those that correspond to some simple physical processes in the bulk spacetime. So in the rest of the talk, I will discuss the solutions that in the bulk spacetime correspond to contact and tree exchange diagrams, which are the two diagrams that we have at leading order in perturbation theory. As I will describe later, the inflationary three-point function can then be obtained by taking a simple limit of the de Sitter four-point function. Okay, so let's first start by looking at contact diagrams. I previously mentioned that all physical correlation functions must have total energy singularities. So the simplest possible 4-point function is the one that just has this singularity and no others. It turns out that these solutions are in one-to-one correspondence with contact interactions in the bulk, where the number of derivatives in the interactions is related to the order of the total energy pole in the correlator. We see that it is very easy to obtain higher order solutions from the boundary perspective, which can be done simply by acting with the derivative operator delta U multiple times on 1/E. Notice that there's also a nice similarity with the structure of contact diagrams in flat space, where the amplitudes are just given by a polynomial of the Mendelssohn variable S. The correlator with the next simplistic analytic structure corresponds to the tree exchange diagram. It turns out that this diagram satisfies two ordinary differential equations, which state that acting with this particular differential operator on the left-hand side returns a contact diagram on the right-hand side, where m here stands for the mass of the intermediate particle. Again, it's quite amusing to see that this equation very much resembles the structure for amplitudes in flat space, in which case multiplying the tree exchange amplitude by the inverse propagator results in contact diagrams on the right-hand side. We see that this delta U factor plays the role of the Mendelssohn variable S, but unlike amplitudes in flat space, obtaining de Sitter correlators requires solving a differential equation. Fortunately, because the tree exchange correlator satisfies a relatively simple ODE, we actually have a chance of solving this equation. Because it's a second order equation, to fix the solution, we need to impose two independent boundary conditions. We can impose this condition by demanding a specific behavior of the solution in special kinematic limits. One of the limits we can take is the so-called folded limit, for which two of the external momenta become collinear. The general solution has a singularity in this limit, but for correlators that start from the Bunch-Davies vacuum, it is well known that this singularity should be absent in this limit. Another special kinematic limit we can look at is the so-called collapse limit, in which the intermediate momentum is taken to zero. This is the limit in which the intermediate particle becomes long-lived, so the solution in this limit behaves as a product of two 3-point functions on each side of the 4-point function. Our task then boils down to finding the solution that is conformally invariant and satisfy the previous differential equation, as well as being consistent with all these behaviors in these singular limits. Let me now present the final solution for the exchange correlator for simplicity in the U limit, a small U limit, but the general solution has essentially a similar behavior. The solution consists of two parts: the particular solution, which is an analytic function that can be Taylor expanded around U equals 0, and the homogeneous solution given by a non-analytic oscillating term. Looking first at the series solution, we see that the coefficient of the series is suppressed by 1 over mu squared or h squared over m squared in the large mass limit. This power law suppression is what we expect from taking an EFT expansion, meaning that this part of the solution captures the effect of integrating out the intermediate massive particle. The second term is physically more interesting, which describes a non-perturbative correction due to particle production that cannot be captured in the EFT. This can be seen from the overall 1 over Cauchy factor that becomes an exponential Boltzmann factor for large masses. In particular, as we'll see, the oscillatory behavior is a fingerprint of the time evolution of massive particles in the bulk and provide a phenomenologically very interesting signal that we can look for in observational data. So far, we've looked at the analytic structure of the 4-point function of conformal scalars in exact de Sitter space. So let me now describe how to generalize this result to the actual inflationary correlators of our interest. Since the observed fluctuations are nearly Gaussian, our main experimental targets are not the 4-point function we've looked at, but rather 3-point functions, or the bispectra, involving a mixture of the scalar and tensor fluctuations, zeta and gamma. Fortunately, we don't have to resolve the equation for these individual correlators, but there's a simple procedure we can take from the previous solution of conformal scalars to inflationary correlators. Specifically, there exist certain differential operators that changes quantum numbers of external and internal fields, which can be constructed in a systematic way using known techniques in conformal field theories. Finally, we can obtain the desired bispectra by simply taking a soft limit and sending one of the external momenta of the 4-point function to 0. So the upshot is that once we know the simplest correlator for conformal scalars, obtaining all the rest of the correlators becomes an exercise of constructing corresponding differential operators for which there exists a systematic algorithm. For the bispectrum, the characteristic signature of extra particles becomes most prominent when taking the squeeze limit, that is, taking the limit in which one of the 3 external momenta is small. The main features in this limit include the oscillatory behavior of as a function of the mass of the intermediate particle, and the 1/, cost factor indicating physical particle production, as we saw before. Also, it has the distinctive Legendre polynomial dependence that encodes the spin of the intermediate particle. To summarize, the unique shape of the 3-exchange bispectrum in the squeeze limit allows us to easily read off the masses and spins of the extra particles that couple to the inflaton by measuring the angular dependence and the oscillatory behavior. A picture is worth 1,000 words, so finally, let me show you a visualization of the behavior of the correlator. For comparison, the left panel also shows a familiar plot of the cross-section with a resonance that indicates the production of a heavy particle. We see that the shape smoothly transitions from a polynomial behavior at low energies dictated by the EFT expansion, and then develops the resonance when the center of mass energy reaches the threshold for producing the heavy particle. The right panel, on the other hand, shows the behavior of the 3-exchange cosmological correlator as a function of the momentum ratio. As I described, the presence of these oscillations in the squeeze limit is the way these correlators encode particle production during inflation, and the period of these oscillations in log k is precisely fixed by the mass of the particle. The shape away from the squeeze limit is instead dictated by the EFT expansion. One important thing that I would like to highlight is that making a precise prediction for the transition between the EFT and oscillatory shapes is only possible if we know the full solution for the correlator. Our formalism should therefore help constructing exact templates that encapsulates all available Fourier modes from observations, not just in special kinematic limits. Okay, so let me now conclude with an outlook. Hopefully, I've convinced you the usefulness of the bootstrap approach to cosmological correlators, as well as its intriguing connection to the physics of scattering amplitude. Moreover, since conformal symmetry plays a crucial role in our story, our formalism shares many theoretical tools that are already well established and widely used in the study of conformal field theories in the context of ADS-CFT and the conformal bootstrap. So I think this research direction is a very exciting one and has many interdisciplinary implications, with an especially important application to observational cosmology. As the final slide of my talk, let me show here an incomplete list of open problems, some of which being currently worked on by us as well as other groups. And with that, I'll stop here. Thanks for listening.